As part of our engineering program at Télécom Physique Strasbourg, we were asked by the German company Trinamic Motion Control to showcase their product. Our client creates integrated circuits for motion control, so our project consisted in creating a self-balancing robot, allowing them to demonstrate the capacity of their chips to be suitable for an application on a small battery-operated robot. Our self-balancing robot was built around the TMC7300, one of Trinamic's new motor driver allowing the control of two motors. The first part of the project was to create a robot that can stand in balance with only two wheels. The second part of the project was to be able to control it remotely with a mobile application so that it could move.
We then defined a specification for the robot which had to be stable and move easily, while being compact and responding quickly to orders given. The application had to connect the user to the robot with a simple graphical interface, while sending back data such as speed and battery level to the user. As this project is quite large, we divided the project into 4 parts to move forward in parallel efficiently: the electronic part for the choice of components and their use, the design part for the design of the robot model, the automatic system part for the modeling of the balancing, and the programming part for the implementation of the balance and the code of the application.
In addition to the motor driver provided by our customers, our robot needed wheels and the motor to run, small enough to keep the robot compact but also powerful enough to make the robot move. A gyroscope was also needed to measure the inclination of the robot and to adjust its balance. The servo control was managed by the low P4 microcontroller, which also has an internal Wi-Fi antenna to control the robot remotely. The design was made on SolidWorks, importing the 3D model of the other component to ensure the accuracy of the measurement. The robot has 2 floors. The first prototype, the components are placed on both floors. On the final prototype, the components are gathered on a PCB, which was realized by the team of the Eagle software. The PCB will be on the second floor. The support was realized in 3D printing and the plexiglass was cut by laser printing with the FabLab equipment.
So the control theory of the robot is done by implementing an automatic cascade of 2 correctors. To do so, we've done the modelization of the robot on MATLAB by taking into account all the parameters of the system. Next thing, we did the simulation on Simulink to test the correctors' parameters. After ending the theoretical part, we implemented the code on Arduino IDE that is compatible with our microcontroller, the low P4. So in order to command our robot, we developed an application on Android Studio with Java and XML. So it contains the main menu where you can give speed and direction instructions.
When the robot starts up, it connects to Wi-Fi, and if the connection is established, the LED located on the low P lights up, and so the user can control the robot via the application by controlling its speed. The robot can only move forward, backward, or stay in equilibrium, and if the Wi-Fi connection is lost, the robot stays up and stable. The robot is powered by battery which are located under the robot and are easy to access.
This project was a real opportunity to develop technical skill. Indeed, this complete project required to know how to make a computer-assisted design, to know how to program an application, to know how to model a balance, and to have the necessary knowledge in electronics for the circuit. This project was also a first approach of the engineering profession on a social level because we learned how to lead a project in team and to progress effectively on the project as part of a group.